Уважаемые коллеги, наш форум
Dear
продолжает.
colleagues, we are proceeding with our deliberations. So laureates of the Nobel Prize and the Prize of Wolf and Cabri, and so they are participating in that Congress. And you may put a question to the leading scientists of the world. What about the analytical models of machine learning? And is it possible to practically implement those challenges? Is it possible to work with the material as a component of the engineering design? What about startups in terms of mathematical modeling of the materials and processes? And experts are going to share their expertise with due regard to their significance in the sphere of specific industries. And the role of modeling and simulation is going to be discussed now. I would like to pass the floor to Alexander Fertman of Skolkovo Foundation, the Director for Science and Technology and Education. Good afternoon, dear colleagues. I do hope that the communication is good and the connection will be reinstituted. Are we going to see our speakers, dear colleagues? I'm going to speak Russian. And as soon as I see our speakers, I will talk English. Please, can you hear me? Krzysztof, can you hear me?
Yes, I do.
Professor Matiszewski.
Yes, I do. That's all right.
I'm pleased to introduce to our brilliant speakers laureates of Wolf medals, Krzysztof Matiszewski, Warner University Professor of Natural Science, Department of Chemistry, Carnegie Mellon University, and Hollis Professor of Mathematics at Natural Philosophy, Emeritus, Harvard University, Bertrand Halperin. Hello.
Hello.
Discovering new materials is an important part and very important direction for the development of science, technology, and innovation worldwide. The last few decades have seen the discovery and development of a large number of complex materials having extraordinary and unique features, both hard and soft, including shape memory alloys, carbon nanotubes, graphene, nematic elastomers, liquid crystals, colloids, polymer fluids, and others and others. And today we want to ask our experts to share their vision on the frontiers of development of new materials, how new materials will influence on our life, and how mathematical modeling can help us to develop new materials. Please, Professor Matiszewski, you will start from soft part.
All right, let me just start sharing my screen. And
yes, we see your screen.
Yes. And before doing that, I would like to say Здравствуйте or Dobry wieczór in Moscow. So I will try to tell you today about both how polymers can be made and also how they can be used for some advanced applications. So if you look at the graph, which is on a left side, just a second, let me put a pointer. You could see here pretty dramatic increase in the number of volume or weight of polymers produced. So when I was born in 1950, it was 1.5 million ton per year. When I got my PhD, it was already 45 million tons per year. And now it is 368 million ton per year. So if you divide this number, which is 368 billion kilograms per year by billion people, it would be approximately 1 kilo per week per person. So it is a really huge amount of polymers made in those days. Very often they are used as commodities, and sometimes it's a problem what to do with them. But this dramatic increase in the production of polymers is really related on one side to how easy it is to process them, and also many of the special properties. They are lightweight and they are pretty versatile. So if you look at automotive industry, for example, or aviation, without polymers, it would not be possible to have the modern cars, because 50% of the weight of a car is now a polymer, whether it would be inside or it would be a body with the fenders and other part of the body. Without carbon composites, it would not be possible to have modern aviation. So no Dreamliners, no Airbus 380s. If you want to win a medal in Olympics, you must think about how to use a specialized equipment for it. Sometimes polymers are stronger than steel. And without polymers, it would be no computers, no integrated circuits, no iWatches, no iPads. If you think about the drugs, 21st century is a century of the polymeric drugs, which will target particular cells, for example, tumor or cancer cells, and then they would deliver a toxic drug inside this tumor or a cancer cell. If you think about the COVID-19, polymers are not only used for gloves and masks or respiratory equipment, but also to pack messenger RNA, which is in fact also a polymeric, natural polymeric material in a polymeric lipids. So I will tell you today how one can make some advanced polymers using radical polymerization. So this is the most common way of making polymers. And in fact, the production of polymers relies on these free radicals, which very rapidly react with a monomer with a fraction of maybe 1 millisecond. And they terminate after approximately 1 second.
I'm sorry, we see you, but don't see your presentation. Can you share with us your presentation?
Yes, I share and I can stop.
I see the presentation.
Yeah?
I see it.
Okay, then it's our mistake. Okay, we will try to find. Thank you. Please continue.
Yeah. So really what was discovered, which we made 20 years ago, that we extended life of a propagating chain from seconds to approximately hours or even days by equilibrating in a dynamic way these radicals with dormant species using various types of catalysts. And during last 20 years, we developed catalysts which are 1 billion times more active than before. And we continuously regenerate these parts per million of catalysts using some kind of a mild reducing agent, something like vitamin C, ascorbic acid, sugars, but sometimes also electrical current or light. And of course, it is not only the way to make homopolymers, but make various nanostructured materials with complex architecture, including, for example, bioconjugates combining proteins with polymers or nucleic acids with polymers, grafting polymers from surfaces of nanoparticles or flat wafers. And I should say that we are quite lucky because we interacted with many companies. We have a consortium of 60 companies at Carnegie Mellon, and we signed so far 17 industrial licenses to make these polymers commercially, as well as some specialty materials. So if you look at the development of the atom transfer radical polymerization, which we invented, and some other controlled radical polymerization processes, you could see here a number of papers which dramatically increases during the last 25 years. So around 25,000 papers were published on ATRP, maybe on average 3 papers per day in nowadays. If you look at a Google and enter ATRP, it would be 8 million entries. Also pretty large activity in industry, as you could see by number of patents. So these are materials made for high specialties, advanced materials like coatings, cosmetics, nanocomposites, electronic materials, biomaterials. But being in a 21st century, we need to think about sustainability, about recycling, and polymers from renewable resources. So what can we control in a polymeric structure? On one side, we can control shape of a molecule, meaning not only linear chains, but also rings, stars, comps, and precisely controlled networks. And combining really two or more comonomers can lead to statistical copolymers, segmented block copolymers, gradient copolymers, periodic copolymers, and putting functionality in many parts of a molecule to construct, for example, polymers with two different compositions, like a microarm stars, pom-pom, cyclic structures, and some others. So I wanted to show you some results of the collaboration which I have with my Russian originally colleague, Sergei Sheiko, who is a professor at University of North Carolina. And we try to really make materials which are very different than what you know so far. So this is an example of a molecular brush, which we construct by making a backbone first, and then growing polymer chains on the sides of this, what we call bottle brush, because it is extremely densely grafted structure. One from another side chain is at a distance of 1/4 nanometer. So in solutions and also on a surface, they look like a bottle brushes, which I used to clean test tubes, so used to be cleaning the corresponding, let's say, milk bottles. Of course, if you think about the dimensions of this typical bottle brush, 10 centimeters, and what we make 100 nanometers, it would correspond like 10 centimeters to 100 kilometers, meaning like distance from Prabimovo and Skolkovo to the center of Moscow. So why we are interested in this material? So maybe to tell you that every polymeric material below its glass transition temperature is pretty tough and pretty strong, having modulus in a range of 10 to the power 9 Pascal. But if you increase temperature above this glass transition, then these polymers get softer, very segmental relaxation, and sometimes they reach a rubbery plateau, and this is something when you make a rubber, which will have a modulus